Okay, so the main difficulty here so far was just the notations. So note that this horrible expression belongs to the eigenspace lambda v lambda I. Yeah, I kind of had to hesitate. Notice that these lambdas and these are very different. These are eigenvalues and these are just scalars. It might have been better to use a different letter besides lambda. And let's denote this by ui. So let's denote. So this means that what we actually have here is a sum of ui's that's equal to 0, where each of the ui's are in the eigenspace v lambda I. So note the eigenspace, or the decomposition of the eigenspaces as a direct sum implies the following. It implies that ui is actually equal to 0 for every I between 1 and k, excuse me. And this is a general fact of direct sums. It really has nothing to do with eigenspaces. Okay, but it's a useful property that eigenspaces form a direct sum. But what does this mean? Well, what is ui? Let's go back. ui is just a direct sum over here. Okay, again, we have I going from 1 to k. You can just think of I as constant for a moment. But these are vectors in the ith basis, right? So therefore, from the linear independence of the basis vectors in Bi, we obtain that the lambda ji's are all 0. They're all 0. Now j runs from 1 to L1, and the i's run from 1 to k. And that means we proved linear independence, right? If we go back up to the initial expression, that means we proved that all of these coefficients, all of them are 0. Therefore, we've shown that B is linearly independent. So the difficulty here is really the level of abstraction and the notations. So I really do suggest that you try to solve this for only 2 bases, like B1 and B2. And then it's just a little bit more readable. So therefore, B is linearly independent. So it might be a challenge to understand the proof, but it's absolutely correct. But we did use the direct sum decomposition of eigenspaces, right? That's a fairly non-trivial result. Okay, so have an amazing day and happy linear algebra.